Welcome to the Public Exam Review for Chapter 8 on Logarithmic Functions. In this presentation, we will look again at the transformations of logarithmic functions, Part 2. Here we will focus on sketching the graph of a logarithmic function by applying a set of transformations to the graph of y equals the log of x to base c, where c is greater than 1. And we will also state the characteristics of the graph. Here we will look at the transformations of a logarithmic function. We will use transformations to sketch the graph of y equals a negative in front of the log of x minus 1 to base 2 plus 4. Notice to begin with that the base equation for this logarithmic function would be y equals the log of x to base 2. So it is the value of c, or the base to your logarithm, that indicates what the base function is going to be. So to begin, I have sketched the graph of y equals the log of x to base 2. In order to graph this function, remember that we convert it to exponential form, where 2 raised to the power of y is equal to x. Y is the independent variable, so we assign a couple of negative values, 0, and a couple of positive values to y, and we solve for x. So when y is a negative 2, 2 raised to the power of negative 2 is 1/4. 2 raised to the power of negative 1 is a half. When y is 0, x will equal 1. When y is 1, x will equal 2, and when y is 2, x will equal 4. So these points have been plotted on the base graph of y equals the log of x to base 2. So now we will apply these transformations. But before we begin to apply the transformations, let's list the transformations that occur. When we see a negative sign in front of the log, we know then that there has to be a vertical reflection in the x-axis. The x minus 1 indicates that there has to be a horizontal translation equal to 1 unit to the right. And the plus 4 at the end here indicates a vertical translation equal to 4 units upward. So those are the transformations that occur. I recommend that we use a mapping rule to sketch the graph, where xy comes from the base graph and it will get mapped onto you have to use opposites of reciprocals for the x variable. So if we see x minus 1 in the equation, then the mapping rule will be x plus 1. With regard to the y, the negative is there for the vertical reflection, and it will be just simply y plus 4. So now, we have to choose points from this base equation in order to get the points on the graph of the new function. So we can begin by choosing the point 1 and 0. The point 1 and 0 will get transformed to the point 2 and 4. And another thing that you should remember as well, if we have a horizontal translation of 1 unit to the right, the vertical asymptote, which occurs on the base function, namely through x equals 0, will now get moved 1 unit to the right. So you will have a new vertical asymptote through the point, through the value where x is equal to 1. So that also helps to guide the shape of our graph. If we take the coordinates 2 and 1 from the base graph, 2 plus 1 is 3, negative 1 plus 4 is also 3. So the point 3, 3 has to be on your new graph. As well, we will take the point 4, 2, and that will get mapped onto 5 and a positive 2. So 5 and 2 is there. And that gives you the shape of your new function. So it approaches that vertical asymptote. It will get very, very close to it. But the graph then will veer off to the right. And that's the graph of our new function. We can also, at this point in time, talk about the domain and the range and the equation of the vertical asymptote. So notice that the domain is dependent upon the horizontal translation that took place. All values of x in the domain are x greater than 1 where x belongs to the set of real numbers. As well, we talk about the range, and there are no restrictions on the values of y. Y belongs to the set of real numbers. And then the equation of the vertical asymptote. The vertical asymptote occurs through x equals 1. And those are the characteristics that describe this graph. So now, there are times when we are asked to determine the x and the y intercepts of a logarithmic function. So I thought it would be worthwhile to cover that and show you how to algebraically determine that. When we are looking for x-intercepts, remember that we have to let the value of y equal 0. So then we would have 2 times the log of 3 outside of x minus 1 to base 3 minus 6 is equal to 0. Now we need to solve for x. So we bring the value of 6 to the other side. And we could also multiply 3 times x minus 1 as 3x minus 3 to base 3 equal to 6. Now what we need to do is divide both sides of our equation by 2. So we're just trying to isolate the term that contains the log. So then we are left with the log of 3x minus 3 to base 3 is equal to 3. In order to solve for x, we need to convert that to exponential form. So to convert from logarithmic form to exponential form, you start off with the base to your logarithm. So you have 3 raised to the power of 3 is equal to 3x minus 3. 3 cubed is equal to 27. You can bring the minus 3 over to the left to be plus 3 equals 3x. So then we have 30 is equal to 3x, and that means then that x is equal to 10. So that is the value of x for your x-intercept. And you can write it as the coordinate 10 and 0 if you had to sketch it on a graph. As well, we have to algebraically be able to determine the y-intercept. So if we are looking for the value of the y-intercept, we have to let x equal 0. Let x equals 0 and solve for y. So then we would have y equals 2 multiplied by the log of 3 times 0 minus 1 to base 3 minus 6. So we have y equals 2 times the log of 0 minus 1 is a negative 1 times 3 is a negative 3 to base 3. So in this case, and then minus 6 at the end, you cannot take the log of a negative number. That is not possible. So what that tells us then is that there is no y-intercept in this particular example. Okay, let's look at some examples that could potentially be asked on a public exam. Which function best represents the graph shown below? So here we have a graph that represents some form of a logarithmic function. Notice that the base graph for this function should be, the base graph would be y equals the log of x to base 4. So converting that to exponential form, we have 4 to the y is equal to x. And some points that would be on that base graph. Again, you could pick a couple of negatives and a couple of positives if you like. So I'm just going to take, when y is a negative 1, x would equal 1/4. So you have the point 1/4 and a negative 1. If you have y to equal 0, then the value of x would equal 1. If the value of y is a positive 1, x is going to equal 4. So the point 4 and 1 would be on your base graph. So just to sketch the base graph for a moment, that's what the graph of y equals the log of x to base 4 looks like. So now let's talk about the transformations that have occurred. Notice that first of all, we need to determine if any reflections exist. And in this case, I can see that there has been a reflection in the x-axis. So if I take the purple graph there and I reflect it in the x-axis, this is what the new graph would look like. So a reflection in the x-axis results in y equals a negative in front of the log of x to base 4. So we see there that we had a vertical reflection in the x-axis. So that eliminates two multiple choice answers, C and D, because the only ones that contain the negative in front are contained in parts A and B. Now, if you look at the dotted graph that I have here, notice that that has been shifted or translated horizontally 1 unit to the left. So you also have a horizontal translation equal to a -1 unit to the left. So that means then that the resulting equation will be y equals a negative in front of the log of, that would be x minus a -4 to base 4. And that equation then corresponds with, sorry, I meant 1 there. It's 1 unit to the left. So it's x minus a -1. So that equation then corresponds with B as your multiple choice item. The equation, the x minus a -1 becomes x plus 1. In the next example, which function results when the graph of y equals the log of x to base 4 is transformed by applying the mapping rule, where xy comes from the base graph and it's mapped onto 1/3 x minus 4 and a -5y plus 1. Noticed in all examples that there is no base to the log given, so we know, or we understand that to be a common logarithm with a base of 10. So let's take the mapping rule and convert it then. So we have y equals the log of, that's supposed to be a base 4 logarithm there for each one of these cases, because the graph of y equals the log of x to base 4 is what's transformed. So then, if we're transforming y equals the log of x to base 4 using the mapping rule, let's take care of the x's first. When we see 1/3 in the mapping rule, we know that there is a horizontal stretch equal to 1/3. Therefore, the value in front, or the value of b in front of the x, will equal the reciprocal of that. So we will have y equals the log of, that will be 3 multiplied by, and if we have x minus 4 in the mapping rule, that tells us that we had a horizontal translation equal to a -4 units to the left. So you will see x plus 4 in the equation. Then we have a negative there in front, so we had a vertical reflection in the x-axis, which tells us that the leading coefficient A is negative. So you will see a negative value in front of the log. As well, we have a 5 in front of the y, so that tells us that there's a vertical stretch equal to 5. So in front of the log then, we will see the coefficient a -5. And then the plus 1 at the end will also have a plus 1 in the equation, which represents a vertical translation of 1 unit upward. So the equation that resembles this function is as follows. And that answer corresponds with D as the multiple choice answer. In example 3, it's asking which graph represents the function y equals A times the log of B times x minus h to base 3 plus k. If A is greater than 0, B is greater than 0, H is greater than 0, and K is greater than 0. So what do each of these parameters represent? If A is greater than 0, that tells us that there has been no vertical reflection in the x-axis. So if we start off with any base graph, namely in this case it will be y equals the log of x to base 3, the graph will pass through the point 1 and 0, it'll pass through the point 3 and 1, and it will have a vertical asymptote that looks similar to this. Okay, so that's the base graph of y equals the log of x to base 3. So if there's no vertical reflection in the x-axis, the graph will stay as it is. However, if the value of b is less than 0, then we have a horizontal reflection in the y-axis. So the point 1, 0 will get mapped onto a negative 1, 0. The point 3 and 1 goes to a negative 3 and 1. And the graph will look something like this. So that's the graph there that results when b is less than 0. When h is less than 0, h is greater than 0, that means that we have a horizontal translation to the right. So we have to take this equation here and we'll just move it to the right somewhere. It doesn't really matter where, but everything in the graph has to be moved to the right. So that's a result because of h greater than 0. And then if k is less than 0, we have a vertical translation downward. So we have to take that graph and we have to move it down. So that's the graph that results when k is less than 0. And this answer then corresponds with A as a multiple choice answer. You have to understand what each of the parameters represent and how they affect the base graph of a logarithmic function. In example 4, we are asked, what is the domain of y equals 3 times the log of a negative 2 outside of x minus 4 to base 2 plus 7? When we are asked for the domain of a function, it is important to remember that it pertains to the values of x. So we can algebraically determine that a negative 2 outside of x minus 4. It is important to remember that you cannot take the log of 0 or the log of a negative number. Therefore, a negative 2 times x minus 4 must be greater than 0. So if you distribute the negative 2, you have a negative 2x plus 8 is greater than 0. A negative 2x is greater than a negative 8. When you divide both sides of an inequality by a negative number, it is important that you remember to change the sign. And that's exactly why I chose this question. So you have x has to be less than 4, and that would represent the domain of this function. So that answer then corresponds with B as your multiple choice answer. So remember that when you have a negative 2 and you're dividing both sides of an inequality by a negative number, you have to remember to change the sign from greater than to less than. In example 5, we are asked to use a mapping rule to sketch the graph of y equals the log of a negative 3x plus 9 to base 3 minus 2. We are asked to state the domain, the range, and the equation of the vertical asymptote, and then we will algebraically determine the coordinates of the x and the y intercept. First of all, we need to look at rearranging the terms of this equation so that we have y equals the log of. We need to remove a negative 3 as a common factor, and that would be outside of x minus 3. Minus 2, and the base to your logarithm is 3. So the reason we removed the negative 3 is so that you can see that there is a horizontal reflection in the y-axis. We have a horizontal stretch equal to 1/3, and we have a horizontal translation of 3 units to the right. We will also have a vertical translation of 2 units downward. So once we have the equation in the proper form, then you can write a mapping rule to sketch the graph. So the mapping rule in this case would take x, y, and map it onto a negative 1/3 x plus 3 and y minus 2. Remember that the base equation, which we are transforming here, is the graph of y equals the log of x to base 3. So we have to know some of the points that are on this base graph, keeping in mind that 3 to the y is equal to x. So we have the coordinates, when y is a negative 1, we have the coordinates 1/3, and when x is a negative 1. We also have the point when y is 0, x will equal 1. When y is 1, x will equal 3. When y is 2, x will equal 9. So we can plug these points into the mapping rule to get the equation of our new graph. Because we have a horizontal translation equal to 3 units to the right, we can begin drawing this graph by sketching the vertical asymptote, which will occur through x equals 3. So there is our vertical asymptote through x equals 3. And now we can plug points from the base graph into the mapping rule. So we would have 1/3 and negative 1. So you have negative 1/3 times 1/3 is a negative 1/9 plus 3. So that's going to give us what? 2 and 8/9. And negative 1 minus 2 is a negative 3. So you have the point 2 and 8/9, which is very, very close to the left side of that asymptote, and a negative 3. You have the point 1 and 0. That will get mapped onto negative 1/3 times 1 is a negative 1/3 plus 3 is 2 and 2/3. And 0 minus 2 is a negative 2. So 2 and 2/3 and a negative 2. Then you have the point 3 and 1. And negative 1/3 times 3 is a negative 1 plus 3 is 2. And 1 minus 2 is a negative 1. So the point 2 and negative 1 will be on the new graph. And 9 and 2, negative 1/3 times 9 is a negative 3 plus 3 is 0. And 2 minus 2 is also 0. So your x and your y intercepts are at the origin. And this is what the shape of this graph would be. I could also pick another point as well. 27 and 3 is on the base graph. So if I plug in 27 and 3, you would have a negative 1/3 times 27 is a negative 9, plus 3 is a negative 6, and 1. So this gives us the shape of our new graph. And it will approach the vertical asymptote, but it won't touch it. So that is the graph of y equals the log of a negative 3x plus 9 to base 3 minus 2. Right now, we can also determine the domain, the range, and the equation of the vertical asymptote. Note the domain are all values of x that are less than 3, and x belongs to the set of real numbers. The range is not affected, so you have the range is any real number. And the equation of the vertical asymptote, we gave that right at the beginning, through x is equal to 3. Now, we know here as well that the x-intercept occurs at x equals 0, and the y-intercept also occurs at y equals 0. However, we were asked to algebraically determine the coordinates of the x and y intercept. Since we don't have enough room on this screen, I just copied it to the next screen so that we could do that. We know what the answer should be. However, let's algebraically determine the x-intercept by letting y equal 0. So we have 0 is equal to the log of a negative 3x plus 9 to base 3 minus 2. We will bring the 2 over to the other side. So you have 2 is equal to the log of a negative 3x plus 9 to base 3. In order to remove the word log, we convert it to exponential form, where 3 squared is equal to a negative 3x plus 9. 9 minus 9 is equal to a negative 3x. So we have 0 is equal to a negative 3x, and the only time that will happen is when x is equal to 0. So that gives us the coordinate for your x-intercept. Similarly, we can determine the y-intercept by letting x equal 0. So then we solve for y, where y is equal to the log of a negative 3 times 0 plus 9 to base 3 plus, that's supposed to be minus 2. So we have y equals the log of a negative 3 times 0 is 0 plus 9 is just 9 to base 3 minus 2. So then we can rewrite the number 9 with a base of 3. The number 9 is 3 squared. Again, subtract 2. The log of 3 squared to base 3 is just equal to 2. And 2 minus 2, we have y equals 0. In this step, I'm just going to write down the property of logarithms that I used in this step. Here we have it in the form of the log of c raised to the power of k, where the base of the log is the same as the base of your power. And the answer is equal to the exponent k. So that's how you algebraically determine the coordinates of the x and the y-intercept. The effects of the parameters then, a, b, h, and k, in the equation y equals a times the log of b outside of x minus h to base c plus k. On the base graph of a logarithmic function, y equals the log of x to base c. Remember that a represents the vertical stretch, and if a is less than 0, you also have a vertical reflection in the x-axis. When the value of b is less than 0, you have a horizontal reflection in the y-axis. Otherwise, the horizontal stretch is equal to 1 over the absolute value of b. H represents a horizontal translation. If H is positive, we move to the right. If H is negative, we move to the left. If K is positive, we have a vertical translation upward, and if K is negative, we have a vertical translation downward. The only parameter, H, changes the vertical asymptote and the domain. None of the parameters change the range. And assuming that the values of A, B, H, and K are all positive, we can use the mapping rule where x, y is mapped onto 1 over b in front of x plus h and ay plus k. So that would be the mapping rule that you would choose for this given equation here. Thank you for your time and your attention. Good luck as you continue your review on Chapter 8.